Are the problems on chapter 23, which deals with electromagnetic induction, alternating currents, transformers, and LCR circuits, amongst many other things. So here is the first question. The first question talks about an EMF is induced by rotating a 1000 turn 20 centimeter diameter coil in the Earth's magnetic field. What average EMF is induced given the plane of the coil is originally perpendicular to the Earth's field and is then rotated to be parallel to the field in 10 milliseconds. So here is a coil. It has 1000 turns and its diameter is 20 centimeters. First, it's kept perpendicular to the field. So that means all of the magnetic flux is passing through the coil, but then it's made parallel, so no magnetic field passes through it. So from perpendicular it goes to parallel. So we know that the maximum field is given by the form. You can see the diagrams there. So in this situation, that's maximum magnetic field passing through it, and here there is nothing, zero. And the radius is, of course, half of the diameter in centimeters and then changed to meter. It's 0.1 meter. The strength of the magnetic field is 5 times 10 to the negative 5 Tesla. And the induced EMF by Faraday's law is given by N times delta phi by delta T. Phi is the product of B and A when it's perpendicular. So B in this case is what's given as 5 times 10 to the negative 5. And the area of this coil is pi r squared. So we can calculate it. We see when it goes from the perpendicular to the parallel, it's the effective area that changes. See, because when it's kept perpendicular to the field, all of the field or all of the area is effective. But then when it's made parallel, zero area is effective. So when we consider that, we know that the number of turns is 1000. The Earth's magnetic field is 5 times 10 to the negative 5. And then area is pi r squared. So pi times the radius, which is 0.1 squared, divided by the time. All this happens in 10 milliseconds. And 10 milliseconds is 10 times 10 to the negative 3. So when we account for all that and calculate, we get 0.157 volt. 0.157 volt. Now here is problem number 2. But when the problem says referring to the situation in the previous problem, it's not actually the problem before this. The previous problem had a definite voltage induced, and after we get the induced voltage, we are asked to calculate the current in the ring if the resistance is given, and then the power. Okay, so let's move on. Let's do the A part. Once you have the voltage, you just divide it by the resistance to find the current. And this diagram actually gives the previous situation that it's referring to. Okay, and which is where when the switch is closed, the current begins to build up through the circuit, and when the current builds up, the magnetic field changes, which induces an EMF or a current in this neighboring coil. So that's the previous situation. But anyways, the current is the induced voltage divided by the resistance, and in that previous problem, the induced voltage was 3.04 times 10 to the negative 3 volt. So divide by the resistance, to get the answer as 0.304 ampere. 0.304 ampere. And in B, we are asked to find the average power dissipated. Now, power in this particular case is calculated using I squared R, where I is the current that we just got, and R is the resistance. And the resistance is given here. So multiply that, and we get 0.924 milliwatts. Now, milli is 10 to the negative 3. And in C, we are asked to calculate the magnetic field induced at the center of the ring, for which we go to the formula for magnetic field in the center of a ring due to a current flowing through it. So that formula is mu naught I by 2 times the radius. Mu naught is the permeability of free space, which is 4 pi times 10 to the negative 7. The current in this case is 0.304 ampere, and the radius is, in that previous problem, the radius was given as 1.1 centimeters. So that's where I'm getting that from. So when you calculate, you get 1.74 times 10 to the negative 5 Tesla. And there is a D part where it asks for the direction of the induced magnetic field due to the MRI's field. So looking in the direction of the coil, we apply the right-hand rule in order to find the direction of the magnetic field. So when we look in the direction and use the right-hand rule, the induced current is counterclockwise. The induced current is counterclockwise, and you know the right-hand rule. If the thumb gives the direction of the current and you hold it in the direction of the current, the induced magnetic field is given by, the closed fingers towards its tips. So if the current is flowing that way, you have the magnetic field coming that way. But if the current is flowing opposite, then you hold it opposite. You see the current flowing opposite. Now you have the magnetic field also reverse the direction. So that's how we do that. And then we have this problem where a jet airplane with a 75-meter wingspan is flying at 280 meters per second. What EMF is induced between the wings if the vertical component of the Earth's field is given? Now, the vertical component of the Earth's field is perpendicular to the ground, that way, and the airplane is flying horizontally, so that way. So it's very clear that the airplane, let me hold it this way, that the airplane is cutting across the field. It's cutting across the field. That's why we use the vertical component. And in order to calculate this, the formula is B times the length times the velocity. So all those three terms are given. The vertical component is what you mean by B, and that is given. And then you have the length in meters, and the speed is also given in meter per second. So all the units are consistent, and we get 0.630 volt. And in the B part, it says, is an EMF of this magnitude likely to have any consequences? Well, you can see that it's a real small EMF or real small voltage, and therefore it will have no consequences because it's extremely small. In this question, number 4, we have to calculate the peak voltage of a generator that rotates its 200-ton 0.1 meter diameter coil at 3600 rotations per minute in a 0.8 Tesla field. Now this is a direct question. You know that in a generator you have a coil rotating in a magnetic field. And the peak value of the EMF depends on the number of turns, on the area of the coil, it depends on the strength of the magnetic field, B, and omega. Omega is the angular speed, okay, so which we'll have to find out. So omega is 3600 revolutions per minute multiplied by 2 pi radians for each revolution. And then remember, 1 minute is 60 seconds. So to get omega, you multiply the number of revolutions per second with 2 pi. So 3600 revolutions per minute divided by 60, will give us the number of revolutions in a second. Then multiplied with 2 pi, you will get the angular velocity, which is 377 radians per second. Once we get that, the peak value of EMF is just the product of NBA omega. So here are the quantities, and again, A is pi r squared. A for a circle is pi r squared, so the radius in meter is given here, okay, for which we have to take half of the diameter, of course, and when you calculate, you get 474 volt as the peak value of the voltage induced in the generator. So we see that if you increase the speed of rotation or increase the number of turns or the area, increase any of these 4 factors, the peak value of the EMF will increase. Now this question number 5 also deals with a generator. It says at what angular velocity in RPM will the peak voltage of a generator be 480 volt if the number of turns, the diameter, and the strength of the field are given. This is a direct application of the same formula, except that we are asked to find omega. So let's do it. E naught is NBA omega. Rearrange to get omega as the subject. And remember that area is pi r squared. So pi times r squared right there, and we will get the answer to be 763.9 radians per second. That's the angular speed at which it is to be rotated. Now, if you want to find out the angular velocity in RPM, then first we have to find the angular velocity in rotations per second and then multiplied with 60. Okay, and remember that omega is 2 pi times f. So omega is 2 pi times the frequency. We're trying to find the frequency here. You know that from the units, omega is what we got, it's in radians per second, and we get the frequency in rotations per second. Now one thing that I forgot to do is to get the actual answer, you got to multiply this with 60, because that's the rotations in a second. To find the rotations in a minute, you got to multiply it with 60. Which brings us to the next question. This question, if the EMF of a coil rotating in a magnetic field is 0 at time t is equal to 0 and increases to its first peak at 0.1 milliseconds, what is the angular velocity of the coil? We'll look at the remaining parts later on, but just from here, when does the first peak appear? The first peak appears after 1/4 of the time period, because you have a peak and then you have the 0 and then you have the negative peak and then you have a 0. So that's one full rotation. So we know that the time that's given is 1/4 of the time period, and therefore T by 4 is 0.1 times 10 to the negative 3 because it's in milliseconds, from which you get the time period simply by multiplying by 4. And then we find omega by using 2 pi by t. So we get the omega, which is the angular velocity. And then says at what time will its next maximum occur. Its next maximum will come one time period after the first peak, because you have the first peak and then you have the next peak, and the time difference is one time period. So just add the time period. For C, what is the period of the output? We already found that to be 0.4 milliseconds. And then D, when is the output first 1/4 of its maximum? So for that, we use E is equal to E naught sine omega t, and we are given that we're looking for 1/4 of the maximum, so that's E naught by 4, and then you get sine omega t as 1/4, and then omega t happens to be 0.2527 radian. Remember to set your calculators in radian for that. Once you get omega times t, you can get t by just dividing that by omega. And E says when is its next 1/4 of its maximum. Of course, after one more time period, it becomes next 1/4. The time period is here, which is 0.4 milliseconds. So add that and you get the answer. That's how we do these problems. A motor operating on 240 volt electricity has a 180 volt back EMF at operating speed and draws a 12 ampere current. What is its resistance? And what current does it draw when it is first started? So the motor is operating on 240 volt. That's the applied voltage. The back EMF is 180 volt. Back EMF is always opposite to the applied EMF. Obviously, that's why it's called the back EMF. So the effective voltage is going to be the difference, and when we divide that by the current, we will get the resistance. So 240 minus 180 by 12 gives 5 ohm as the resistance. And then in the B part, what current does it draw when it is first started? When it is first started, the motor is not rotating. Therefore, there is no back EMF since there is no induction. That means the entire voltage of 240 volt is applied, and therefore the current would be 240 volt divided by the resistance. Resistance is already found to be 5 ohm, so 48 ampere, and we see that that is a dangerously high current, and that's why we need a starter resistance to limit the current at the start of any motor. So that indicates the use of a starter resistance at the beginning. In this question number 8, a cassette recorder uses a plug-in transformer to convert 120 volt to 12 volt with a maximum current output of 200 milliampere. And so what's given is 120 volt, that's the primary voltage. The 12 volt is the secondary voltage, and the output current is the secondary current because the output is the secondary. And we are asked to calculate A, what is the input current? Now, when you look at the ratio, IS by IP is equal to NP by NS is equal to VP by VS. Now notice that it's IS by IP, okay? And so when you rearrange that, you get IP is IS by VP by VS, which happens to be 120 by 12, which is 10. So 0.2 divided by 10 is 0.02 ampere. That's the primary current. Now in the B part, what is the power input? Input is the primary. Power in the input is the product of the primary current and the primary voltage. So P input is IPVP, and that's got to be 0.02. I'm going to change that. So that's 0.02 times 120, which is 2.40 watts. Is this amount of power reasonable for a small appliance? Yes, it is reasonable for a small appliance. Look, I've now corrected this to 0.02 and all is good. Now is the next question. It says a device is turned on and 3 ampere flows through it 0.1 milliseconds later. What is the self-inductance of the device if an induced 150 volt EMF opposes this? So this is about self-inductance, and self-inductance depends on the rate at which current grows or decays. In this case, the current is growing, means increasing, because the device is just turned on. So the EMF equation is E is equal to, that's the induced EMF, is L times delta I by delta T. L is the self-inductance, which is what we are asked to calculate, and everything else is given. So make the self-inductance the subject and rearrange to get E times delta T by delta I. It's going to flip because you're changing directions, and the time is 0.1 milliseconds, which is 0.1 times 10 to the negative 3, or 1 times 10 to the negative 4. So that's why you see the 10 to the negative 4 there, and then divided by the current, which is 3 ampere. So when you calculate, you get 5.00 times 10 to the negative 3 Henry. Henry is the unit of inductance. That could be written as 5 millihenry. Here again in number 10 is something to do with self-inductance. It's a large research solenoid, has a self-inductance of 25.0 Henry. What induced EMF opposes shutting it off? So here you can see it's the current is shut off. It's a decay of current. When 100 ampere of current through it switched off in 80 milliseconds. Again, the current goes from 100 ampere to 0 ampere in 80 milliseconds. So we have the change in current, we have the change in time, or the time, and then we have the self-inductance. So using the same formulas before, E is L delta I by delta T. L is the self-inductance. So that's given us 25.0. Change in current is 100 minus 0, which is 100. 80 milliseconds is 80 times 10 to the negative 3. And when we do the calculations, we get 3.125 times 10 to the 4 volt. In the B part, how much energy is stored in the inductor? The energy of an inductor is 1/2 Li squared. Okay, so we have the self-inductance and we have the current. Self-inductance is 25. The current flowing is 100 ampere, and we get 1.25 times 10 to the 5 joules. In the C part, at what rate in watts must energy be dissipated to switch the current off in 80 milliseconds? So now, at what rate must the energy be dissipated, means thrown out? So we're looking at delta U by delta T, and that is power. Power is nothing but the rate at which energy is used or dissipated. So we have this U which goes to 0, so delta U is just that number divided by 80 milliseconds, which gives 1.56 megawatts. 1.56 megawatts. Now this question number 11 is about a combination of an inductance with a resistance. It's an LR circuit, and we're asked to find the time constant of a 25.0 millihenry inductor that has a resistance of 4 ohm. So both the inductance and the resistance have been given, and time constant is just the ratio of the inductance to the resistance. So the inductance is 25 millihenry, which is 25 times 10 to the negative 3. The resistance is 4 ohms, so when you divide, you get 6.25 times 10 to the negative 3 seconds. So that is the time constant. And if it is connected to a 12-volt battery, what is the current after 12.5 milliseconds? Now, before we try to find the current after 12.5 milliseconds, we have to find the initial current or the maximum current. Now, the maximum current is simply, by Ohm's law, the voltage divided by the resistance. The voltage is 12 volt, the resistance is 4 ohms, so the maximum current is 3 ampere. And once you get the maximum current, we use the formula I is equal to I naught, 1 minus e raised to minus t by tau, where tau is the time constant. And so the maximum current is I naught, which is 3, which we just found out, and then 1 minus e raised to that, which is, because the time is 12.5 milliseconds, you got to divide that by 1000, so you get that, and then you have the time constant as 0.00625. When we do that, you got to take the negative exponential, that one, and then do the math. You get 2.59 ampere as the answer for the current after 12.5 milliseconds. In question 12, find the current through a 0.5 Henry inductor connected to a 60 Hertz 480 volt AC source. So we have to find the current through this inductance. To find the current through the inductance, first we have to calculate its reactance. The inductive reactance depends on frequency and is given by omega times L, or 2 pi FL. So X sub L means the inductive reactance is 2 pi times 60 is the frequency, inductance is 0.5 Henry, so we get 188.5 ohms. Once you get the inductive reactance, we can find the current, because current by Ohm's law is just the applied voltage divided by the reactance. Remember, instead of resistance, we have reactance here. So we get 480 volt, which is the applied voltage, divided by 188.5, which gives 2.55 ampere. And in the B part, got to repeat the process and find the current at 100 kilohertz. So once again, the frequency is now 100 kilohertz. So the inductive reactance is going to change. So you get 100 kilohertz is 10 to the power 5, and 0.5 is the inductance. So now we get a very high resistance, or in fact reactance, and then the current is going to be really small, because 480 divided by that extremely large reactance is going to give a small current, which is 1.53 times 10 to the negative 3 ampere. So that's how we work out the current passing through an inductor. Now in this question 13, what current flows when a 60 Hertz 480 volt AC source is connected to a 0.250 microfarad capacitor? So now we got to repeat the same problem as before, but this time it's a capacitor. So we got to find the capacitive reactance first, which is X sub C is equal to 1 by omega C. Remember, omega is 2 pi times F. So 1 by 2 pi FC. The frequency is 60 Hertz. Capacitance is given in micro, which means 10 to the negative 6. So when we do the calculations, we get 1.061 times 10 to the 4 ohms. So that is the capacitive reactance. And to find the current, we use Ohm's law, voltage by that reactance. Now it's 480 divided by 1.061 times 10 to the 4, which gives a current of 45.2 times 10 to the negative 3 ampere. And again, for the B part, we got to find the current at 25 kilohertz. Frequency is changed, so the capacitive reactance will now change. And as the frequency increases, the capacitive reactance decreases. So this time we get a much lower capacitive reactance. Calculates out to be 25.46 ohms, much smaller than before. And then the current is just 480 divided by that, which will give us the answer, which is 18.8 ampere. So you see, there's a big difference between an inductance and a capacitance. For an inductance at high frequencies, the current is small. But for a capacitance at high frequencies, the current is large. So that's an important difference to be remembered. Here is a very important question. It's an RLC or LCR series circuit. It has a resistance, an inductance, and a capacitance connected in series. Their values are given, and we have to find the impedance at 120 hertz. Now, in order to do this, first we got to find the inductive reactance, then find the capacitive reactance, and use those two to find the impedance. So let's do that. The inductive reactance is 2 pi f times L. So when you do that, frequency is 120 hertz. The inductance is 100 microhenry, so it's 100 times 10 to the negative 6. We get that as 0.0754 ohms. Now, capacitive reactance XC is 1 by 2 pi FC. So 1 by 2 pi times, again, 120 times C is 80 microfarad. Again, that's 80 times 10 to the negative 6. Gets 16.58 ohms. Impedance is given by this formula, square root of R squared plus XL minus XC whole squared. So plug it into that. The resistance is 2.50. That's XL, 0.07540 minus XC squared. When we do that math carefully, we get 16.7 ohms. In the B part, we are asked to do the same stuff again, but at another frequency, namely 5 kilohertz. So again, you got to find XL, you got to find XC, and then find the impedance. All right? So when we do that, these are the numbers that we get. All right, so XL is 3.142, XC is 0.3979 ohm, and the impedance is again the same formula. We get that. Just substitute those numbers and be careful about the calculations. I just forgot to include a square there. Now let me just try to plug that in there right now. So that's a square there, and you get 3.71 ohms. In the C part, if the voltage source is 5.60 volt, what is the IRMS at each frequency? Remember that what's given us the voltage is the RMS value of the voltage, and we are asked to find the RMS value of the current. So just apply Ohm's law, and here it's the same question. The C part, when you apply Ohm's law, you just have to divide the voltage by the impedance. The voltage is 5.60, and the impedance that we calculated was 16.69. So we get that for the first frequency, 0.336 ampere. Likewise, at the second frequency, again apply Ohm's law to get the RMS value of current. Remember, when you are given the RMS value of voltage, you just have to divide it by the impedance to get the RMS value of current. Now this gives 1.51 ampere. D is important. What is the resonant frequency? Resonant frequency is the frequency at which the impedance becomes minimum. Now, and the current becomes maximum. And it's given by the formula 1 by 2 pi square root LC. And we have the inductance as 10 to the negative 7, okay, 10 to the negative 7, and the capacitance is 8 times 10 to the negative 5, and you get the frequency, resonant frequency is 5.63 times 10 to the 4. And what is the IRMS at resonance? I already specified. At resonance, the impedance is just the resistance, because XL and XC become equal and cancel out. So that part becomes 0, and so the impedance at resonance is just the resistance. Knowing that, we just divide the RMS value of the voltage by the resistance to get the current at resonance as 2.24 ampere. Last question in this problem set. An RLC series circuit has, I think it's the same resistance, inductance and capacitance as in the previous problem, but now we have to find the power factor at the frequency 120 Hertz. Let's do that first. The power factor, cosine phi. Phi is the power, so cosine phi is actually the power factor. All right, so cosine phi is R by Z. And so we get the power factor. Power factor is just a number. It has no unit. And we get 0.150. And remember that phi, in this cosine phi, what we call phi, is actually the phase angle. It is the phase angle. So in the B part, we are asked to find the phase angle. Now we got cosine phi. If we know the value of cosine of an angle, you take the inverse of that to find the angle. So the phase angle is the inverse of 0.1550, and I put the exact number that I had in the calculator. That's why you see 0.1498 instead of 0.150. And you get it as 81.4 degrees. And in the C part, what is the average power at 120 Hertz? The average power is given by the formula IRMS times VRMS times cosine phi. So we know the IRMS value, 0.3355. The VRMS value is 5.60. Remember, this is from the previous problem, so we have those, and we have the power factor cosine phi, and so you get 0.281 watts. And D, find the average power at the circuit's resonant frequency. All right, at the resonant frequency, phi becomes 0 because it's only the resistance and it's going to be in phase with the voltage. Phi is 0, so cosine of 0 is 1. So cosine phi becomes 1, and then that means to get the power, you just multiply the IRMS with the VRMS. Or use this. You can use this formula for power. V squared RMS by R. Either way, you get the same answer. So the square of the voltage, 5.60 squared divided by 2.50 gives 12.5 watts. That is the average power at the resonant frequency. You can see that the average power at the resonant frequency is much higher than the power at other frequencies. Why? Because the current is maximum and it's using maximum power at resonance. And I hope you understood how to work out all these problems in this chapter. Good luck for the exam.